Hydraulic shears apply 500 tons of pressure, reaching the Boeing 747's high-tensile 2024 T3 aluminium alloy fuselage structure. Diamond saws cut GE90 nickel superalloy turbine blades, precisely engineered to survive extreme thermal environments exceeding 1600 degrees Celsius. Heavy cranes extract ultra-high-strength steel struts, built to absorb landing forces exceeding 300,000 kilograms per touchdown.
Laminated windshields undergo testing, proving they can withstand 4-pound bird impacts at speeds exceeding 400 knots. Hydraulic actuators are stress-tested, simulating 20,000 operational cycles required over a 20-year aircraft service lifespan. Steel-reinforced tires are nitrogen-filled, preventing internal combustion during the high-friction heat of heavy aircraft landing sequences. The vertical stabilizer's leading edge manages lateral stability and yaw control, ensuring safety during extreme aerodynamic turbulence. High-impact aramid fiber cowlings contain potential engine blade failures, protecting the fuselage from high-velocity kinetic debris. Emergency slides use compressed carbon dioxide to inflate complex nylon urethane structures in less than 6 seconds.
Advanced composite winglets reduce aerodynamic drag by 5%, significantly optimizing fuel efficiency for long-haul global flights.
Carbon-carbon brake discs operate at 3000 degrees Celsius, providing vital stopping power for 400-ton aircraft.
Aerospace-grade titanium fuselage frames form the aircraft's primary anatomy, ensuring pressurized structure.
60,000 psi waterjets dissect carbon fiber composites, separating resin-bonded layers for specialized chemical recycling and reclamation.
System drainage extracts fire-resistant Skydrol LD-4 fluid, which maintains its low-density profile at 40 degrees below zero.
Shredding Grade 5 titanium pylons requires massive torque to overcome tensile strengths of 950 megapascals.
The aircraft's wiring is granulated, recovering 99.9% pure copper for high-grade electrical industrial reuse.
Interior floor panels utilize Nomex honeycomb cores, providing high strength-to-weight ratios under FAA-certified fire-retardant standards.
Triple-pane polycarbonate windows are extracted, built to withstand pressure differentials of 8.6 pounds per square inch.
APU lithium-ion batteries undergo thermal stabilization, preventing runaway reactions during the critical dismantling and recycling phase. Zinc-alloyed 7075 T6 aluminium wing spars are the primary backbone, supporting stresses exceeding 500 megapascals.
HEPA filtration vacuums remove miles of fiberglass insulation, safely containing chemical treatments used for fire resistance. Neutralizing fuel tanks requires dissolving polysulfide sealants, which provide leak-proof barriers against corrosive Jet A1 fuel.
Nickel-cadmium emergency batteries must be carefully processed to reclaim heavy metals while preventing environmental contamination.
Lightweight magnesium alloys from gearbox casings are sorted separately to avoid contaminating the primary aluminium smelting stream.
Lead-acid batteries offer 99% recyclability, where smelted lead plates create new high-capacity industrial storage.
Induction heating releases chromium-plated pins, engineered to withstand extreme shear forces without succumbing to atmospheric corrosion.
Avionics are pulverized to extract rare earth elements and silicon, reclaiming precious metals from flight management computers.
Non-sparking beryllium copper bushings are vital for safety, making them essential in explosive environment mechanical and electrical links.
Aircraft-grade synthetic rubber is shredded and separated, destined for conversion into high-durability industrial flooring and asphalt.
Cabin panels are stripped to separate decorative laminates from aramid fiber cores, providing essential fire-blocking capabilities.
Machined from 6061 T6 aluminium, seat tracks are recovered to maintain alloy integrity for secondary manufacturing.
Halon 1301 fire spheres are safely recovered, with pressurized gas recycled into certified closed-loop systems.
Inconel manifolds are harvested for extreme oxidation resistance, retaining stability at temperatures up to 800 degrees Celsius.
High-density polyurethane seat foams are baled, utilizing their flame-retardant properties in specialized waste-to-energy processing plants.
Galley refrigeration units are drained of R134A, ensuring zero atmospheric leakage of high global warming fluorocarbons.
Heavy-duty stainless steel cargo rollers are magnetically sorted, ensuring the purity of the primary aluminium recycling stream. Fiberglass water tanks are pulverized, with GFRP material repurposed as aggregate for high-strength industrial concrete.
Titanium high-lock fasteners are recovered, providing high-purity metal for specialized vacuum melt aerospace ingot production.
The 747's upper deck floor beams are structural masterpieces, designed to reinforce the aircraft's iconic pressurized crown.
Environmental ducting is stripped, reclaiming lightweight alloys used to circulate pressurized air at temperatures down to sub-zero.
The radar transparent radome is a specialized epoxy glass laminate, engineered to protect avionics without interfering with electromagnetic signals.
Flexible nitrile fuel bladders are extracted and cleaned, repurposed for industrial-grade containment liners and secondary fuel storage.
Nickel-plated brass pitot tubes are recovered intact, representing precision engineering designed to measure airspeed via air pressure.
Miles of high-strength nylon cargo netting are shredded, converting the polymer back into raw pellets for textile manufacturing.
Wing ribs, forged from 705 T6 aluminium, define the airfoil shape and provide vital torsional rigidity.
The flight deck control yoke is salvaged as a mechanical artifact before the final cockpit shredding process begins.
Precision diamond wire saws perform circumferential cuts, sectioning the fuselage into 30-foot modules for industrial transport and shredding.
Titanium-reinforced cargo floor beams are engineered to withstand extreme floor-loading pressures of up to 2,000 pounds per square foot. Stainless steel outflow valves are recovered to reclaim high-grade alloys and precision-machined mechanical actuators from the pressurization system. The horizontal stabilizer's pivot pin is extracted to recover high-strength steel alloy designed for extreme mechanical shear resistance. Emergency lighting batteries are harvested separately, ensuring cadmium-containing cells are diverted to specialized hazardous material recycling streams. Avionics racks, manufactured from 224 aluminium, are processed to reclaim high-purity alloy for sensitive structural applications. Small aluminium check valves are recovered as high-purity scrap, originally designed to prevent fuel slosh during aircraft maneuvers.
Flattening the 2043 aluminium skin increases density, preparing the primary structure for its final transition into the furnace.
Eddy current separators use powerful magnetic fields to repel non-ferrous aluminium from debris with 98% accuracy. Portable X-ray analyzers verify alloy chemistry in milliseconds, ensuring precise sorting between 7000 and 2000 series aluminium.
Industrial hammer mills reduce aircraft sections into uniform fragments, increasing surface area for efficient chemical purification during smelting.
High-speed optical sensors scan thousands of fragments per second, sorting metals based on their exact elemental laser-induced composition.
Dense media tanks utilize calibrated fluid densities to float lightweight aluminium away from heavier contaminants like steel and copper.
Thermal decoding vaporizes aircraft paint at 500 degrees Celsius, removing organic contaminants without melting the underlying alloy.
High-pressure briquetting presses convert loose shavings into dense pucks, preventing metal loss due to oxidation during furnace melting.
Spectrographic analysis ensures the molten batch meets exact specifications, verifying the precise balance of copper, magnesium, and zinc.
Purified alloy is cast into 1,000-kilogram ingots, ready to be rolled into new sheets for high-end industrial engineering. Ultrasonic transducers scan the ingot's internal grain structure, ensuring zero structural porosity before release for high-stress manufacturing.
Titanium boron grain refiners ensure a uniform crystalline structure, enhancing the recycled alloy's fatigue resistance and tensile strength.
Vertical direct chill casting produces high-integrity slabs, utilizing controlled cooling to prevent internal stresses in recycled aluminium.
Precision Brinell hardness testing verifies that the recycled alloy has achieved the specific temper required for structural engineering.
Every ingot is laser-etched with a digital birth certificate, providing full traceability from the retired aircraft to new material.
Automated systems organize thousands of tons of recycled alloy, preparing the material for global distribution across the supply chain.
Packed for international transit, these containers represent the circular economy, where a retired jet becomes the foundation for infrastructure. Recovered materials enter the global commodity exchange, where high-purity aerospace scrap commands a premium over standard secondary alloys. Logistics hubs facilitate the movement of reclaimed metal to manufacturing centers, connecting the Atlantic and Pacific via deep-water ports. This closed-loop process reduces energy consumption by 95% compared to primary aluminium production from bauxite ore. Hot rolling mills transform ingots into high-precision coils, destined for the skin of new aircraft, trains, or electric vehicles.
High-value components are airlifted to global maintenance hubs, keeping the existing worldwide fleet operational instead of entering the shredder.
Digital twin technology tracks the disassembly, providing data-driven insights to optimize future aircraft designs for easier recycling. The facility maintains a zero-discharge system, recycling millions of gallons of water through advanced membrane filtration and UV treatment.
Boneyards are evolving into renewable energy hubs, powering high-energy shredding processes with clean, on-site solar power installations.
Premium structural components find a second life in high-end architecture, preserving aviation's legacy through creative industrial upcycling.
With 99% recycling efficiency, the final residue of a 200-ton aircraft is reduced to a single non-recyclable bale.
As one giant retires, its molecular anatomy becomes the building blocks for the next.